Good afternoon. Let's start our lecture for today. Our second lecture in informatics is the foundations of the system theory and system analysis. The modern world has numerous kinds of systems that influence daily life. It seems there is almost no end to the use of the world system in today's society. Some examples include transport systems, solar system, telephone systems, decimal system, weapon system, ecological systems, space systems, digestive systems, public transport system, central heating system, computer system, information system, etc. Today we'll talk about definition of theory of system and basic knowledge about general system theory. Definition of system theory is a systematic way of understanding a broad variety of events and situations. This is a set of concepts, definitions, and propositions that explain or predict events and situations by illustrating the relationship between them. How do we use this theory of system theory? The system theory provides a conceptual framework and building blocks, provide a common vocabulary, challenge practice wisdom about why, what, and what if, guide practice and its evaluation, for example, variables to measure. This system theory was first proposed by Ludwig van Bartalanffy in the 1940s. Many scientific disciplines could use systems theory in research and theory development and then be able to identify laws and principles which would apply to many systems. In this way, scientists could better communicate their findings with each other across disciplines and build upon each other's work. Systems theory studies the structure and properties of systems in terms of relationship from which new properties and of all emerge. It was established as a science by Ludwig van Bartalanffy, Antonia Rappaport, Kenneth Boulding, William Ross, and others in the 1940s. System theory, in its transdisciplinary role, brings together theoretical principles and concepts from ontology, philosophy of science, physics, biology, and engineering. Applications are found in numerous fields, including geography, sociology, political science, organization theory, management, psychotherapy, and economics, amongst others. The modern world has numerous kinds of systems that influence daily life. Some examples include transport system, solar system, decimal system, and so on. Indeed, it seems there is almost no end to the use of the world system in today's society. In general system theory, there are parallels found in different scientific disciplines, certain principles which are common to all systems, and by identifying these common elements, hopefully knowledge generated in different disciplines to be combined. A systems approach facilitates understanding of complex phenomena by encouraging clustering of information and clarification of relationships between different elements. We all work within and between a variety of systems, such as structural systems, for example, road network, functional systems, academic departments, social system, different work groups, information system, a class or courses. System theory studies the structure and properties of systems in terms of relationship from which new properties or wholes emerge. There are two assumptions in system theory. First assumption, all phenomena can be viewed as a web of relationship among elements. And second assumption, all systems have common patterns, behaviors, and properties that can be understood and used to develop greater insight into the behavior of complex phenomena. First of all, let's give the definition of system. What is a system? A system is a set of objects or elements that interact to achieve a specific goal. A system is more than the sum of its parts. Its properties emerge from the relationship among its parts and from the system's relationship to its environment. Systems are arranged hierarchically, so every system is a supersystem for systems contained within it and a subsystem for systems containing it. All systems are more or less similar. There are different classifications in system theory. Peter Checkland in 1999 divided systems into 5 classes. Natural systems, the example are ecological systems, human beings. Physically designed systems, examples are bridges, different physical machines. Abstract design systems, examples languages, science such as mathematics. Human activity system, examples politics, banking. And fifth, last type of system in Checkland classification is transcendental systems, beyond knowledge or comprehension. The first 2 classes are self-explanatory. One more classification, Balding classification. Kenneth Balding, one of the founding fathers of general system theory, developed a system classification which has been the starting point for much of the subsequent work. He classifies system into 9 types, and this classification is shown at this slide. Due to Balding classification, we have systems as frameworks. Examples are static structures, skeleton, formal company organizations, rocks. Second type of systems in Balding classification is clockworks. Example is different time mechanisms, self-winding clocks, and solar system belongs to the clockworks type system in the Balding classification. Next type of next category of system is cybernetics, elementary closed system with feedback. Example is the thermostat. Open systems, elementary forms of life interact with their environment in order to change their behavior. Genetic societal systems exchange information with other subsystems, animal system, then human system, in the human system, intelligence gives the human system the ability to think about the future, its goals, and how to reach them. Social organization. These are organizations which have their own combined goals and needs. And the last type of system is transcendental, or other systems not yet comprehended. After the classified systems, we need to understand what those systems do. The function of a system is to convert information, energy, or materials or resources into a planned outcome or product for use within the system, outside the system, or both. At the next slide, you see structure of any type of system. What are the basic elements of any system? Due to the system theory, each system consists of environment. It has inputs, outputs, feedback, environment, boundaries. Each system has goal. Each system has control. It system processes information or energy or resources. Let's talk about systems. So systems are goal-seeking, they are holistic, have hierarchy, have inputs and outputs, transform inputs into outputs, consume or create energy, are affected by entropy, have equifinality, and have feedback. Let's talk about each of these features. First of all, systems tend to be goal-seeking, that is, they move in the direction of goal achievement. Each system has its own goal. The primary goal of any system is survival. All goals will be sacrificed in order for a system to survive. There are two types of goals: inner directed goals and outer directed goals. As usual, design strategies are typically outer directed goals. Maintenance strategies are an inner directed goal. Systems without well-defined goals often go in many different directions. Next feature of the system is holistic. This term was proposed by Frederick Hagel, and holistic means that the whole is more than the sum of the parts. At this slide you see that each system consists of subsystems and can be combined in one suprasystem or super system. The whole determines the sum of the parts. The parts cannot be understood if considered in isolation from the whole. The parts are dynamically interrelated and interdependent. So at this slide you see some subsystems. If we combine all the subsystems together, we get one suprasystem or super system. Systems are nested in a hierarchy water systems consist of subsystems and systems operate within environments. Hierarchies permit complex sets of subsystems. A complex system is difficult to understand as a whole. Therefore, it is necessary to divide the system into smaller units, so-called decompose or partition it. Subsystems can be viewed as modules, elements, or organizational departments. Systems can be grouped together to create more complex systems, so-called suprasystems. In some cases, it is sufficient to consider these systems as a system's elements in a higher level system as part of a system hierarchy. At this slide, you see that system transform inputs into outputs. Input is the energy information introduced and absorbed by the system. Output, energy information discharged from the system. And through puts, the transformation of energy information to be used by the focal system to achieve its goal. Next term in system theory is entropy. Entropy is a measure of the amount of disorder in a system. Everything disintegrates over time. Negative entropy is called entropy. Effects of entropy are offset by the system transforming itself continuously. Maintain order through such things as repairs, maintenance, and possibly growing by importing energy. So all the systems create and consume energy. Examples are physical systems, emotional systems. Equifinality is the ability for systems to achieve goals in a number of ways. This flexibility allows systems avoid the effects of entropy. Each system has feedback. For a system to work properly, it must have control mechanism. Feedback is this control mechanism. Control mechanisms for feedback accept information about system outputs, evaluate information using goal-related criteria, use the feedback as additional inputs. Feedback can allow a system to change its direction. Cybernetics is the study of feedback and control. Examining the feedback and control mechanisms of a system will allow you to see causes of system failure. There are two types of the feedback: positive feedback and negative feedback. Positive feedback, if a system has positive feedback, accelerate actions. Feedback loop signals the system is to open and allow more inputs. Negative feedback decelerate actions. Feedback loop signals the system is to close and cut off or reduce inputs. Types of systems. Systems differ from each other related to degree of self-sufficiency, complexity, and adaptability. Closed systems have fixed relationships among system components and no interaction with the environment, limited transactions with suprasystems and subsystems. Closed system does not accept and respond to inputs, fails to receive and exchange the energy or information from outside the system, characterized by very little exchange of the energy information with the environment. Um, if we're talking about closed system, they have less ability to adapt, less goal-oriented. Open system interact with the environment, have dynamic interaction of components, and can be self-regulating. A system that accepts and responds the inputs, receives and exchanges the energy information from outside the system, greater ability to adapt, more goal-oriented. Systems have different levels of being open or closed. A variety of inputs is required to help a system to remain open. Now let's talk about some properties of systems. Equifinality is the principle by which a system can get the same end or goal from various different routes. What is the same inputs can result in the same outputs by different processes. If you, as a subsystem, are required to obtain a book via input from the environment, the boss has asked you to get a book, you may come to the next meeting with the book output. You may have pick up all the bookshop or the library. The results is the same. So different numerous routes to get the same result. Balance. System tend toward a state of non-change called homeostasis. A system must maintain balance or homeostasis if it is to survive. In order to avoid entropy, the fate of a closed system, the system must engage in regulation and control as well as management of its position in the super system. Systems that are most amenable to change are those that are failing. Survival is threatened and successful and can take risks without uh, threatening survival. Change and adaptability as a feature of system. Adaptation, this is ability of the system to discriminate and act effectively in their environment. In order to survive in a changing environment, the system must be adaptable. There are three types of structural change that a system goes through. Progressive segregation is moving toward less interdependence. Progressive systematization is moving toward more interdependence, and progressive decentralization is when one subsystem becomes more important to the system. Non-summativity. Non-summativity is also called synergy. Systems working well experience synergy. Uh, the total system output are greater than the sum of all uh, inputs. Non-summativity is the assertion that the system is a separate entity which is greater than the mere sum of its parts. If 5 people will write down possible solutions to a problem in seclusion, a group consisting of the same 5 people will generate more and better solutions by group brainstorming. Dependence and interdependence. Different systems can be interdependent or independent. Interdependence. What is a change in one part of the system will result in a change in another part of the system. Propagation of change. Independence. Independence is a particular part of the system has some responsibility for some functionally related activity. Ideally, system components should be independent with respect to each other while being highly interdependent internally. Loose coupling of highly cohesive elements. One of the elements of the system is the boundary. Boundary is the region separating one system from another. Boundary defines what is inside or outside the system. Boundary regulates the flow of energy or information entering inputs and leaving the system outputs. The boundary of a system consists of features which define and delineate the system. Environment. The environment is everything that does not belong to the system yet still interacts with the system. The system is inside the boundary. The environment is outside the boundary. Boundaries are the interface between a system and its subsystems or a system and its environment. Friction occurs at the boundaries of the system. The rubber hits the road, then planes take off and land between an agency and its client. By examining the boundaries of the system, we can often isolate the friction and its causes. Interface. The area of contact between one system boundary and another is called an interface. For example, in the country have boundaries which are traversed by roads. The roads could be considered as interfaces which permit countries to interact. System analysis is a problem-solving technique that decomposes a system into its component pieces for the purpose of studying how well this component part work and interact to accomplish their purpose. This part was about terminology of the system. Now let's try to apply this theory, system theory, to biology and to the medicine. Definition given by Norbert Wiener. Cybernetics is the science of communication and control in machines and living organisms. Cybernetics has close connections to biology and medicine. Biocybernetics is the application of cybernetics to the biological science. Biocybernetics plays a major role in systems biology, seeking to integrate different levels of information to understand how biological systems function. The biological system is a set of self-organized, differentiated components or elements that interact pairwise among themselves through various networks and media, isolated from other sets by boundaries called teguments, and those relation to other systems can be described as a closed loop in a steady state. In agreement with this definition, a living organism can obviously be regarded as a biological system, including any individual organism within and the organs that constitute it, um, as well as their organization. So this definition considers biological systems from the living molecular structures up to the levels of organization, including cells, tissues, organelles, organic systems, human beings, races, social aggregations, um, species, and ecological systems. This lecture attempts to propose a general theory of biological systems based on its principal characteristics and hierarchical structure that apply general ideas to biological systems of different sizes using principles based on energy, information, and mass exchange. To do this, a proposed biological system definition is explained in detail. Using this definition and some fundamental propositions, we discuss the hierarchical structure of the biological systems and their structures and fundamental functions, and end with thermodynamic analysis based on the affinity of the systems. In the cybernetics, the signal is considered as information carrier. Any living organism is considered as biological system, information connected by some physical quantity. Mm. So each biological system transmit information or communication. So information is the transmitting system, and each biological system has control. Simple control, simple control means without feedback, and control with feedback or regulation. According to the theory of information, at each level of organization, cells, tissues, organs, and organ system structure is closely related to function. Cells work together to form tissues. Tissues work together to form organs, and organs work together to form organ systems. There are 10 different organ systems in the human body: circulatory, respiratory, skeletal, muscular, digestive, excretory, reproductive, uh, nervous, endocrine. In any system, signal is an information carrier. All of the systems in an organism are interconnected. At this slide, you see example of the circulatory system, and the circulatory system is connected to all of body cells so that it can transport oxygen efficiently. The function of circulatory system is to service the needs of body tissues, to transport oxygen and nutrients to the cells, to transport carbon dioxide and waste products away. For example, the respiratory system and the circulatory system work closely together to deliver oxygen to cells and to get rid to the carbon dioxide the cells produce. The circulatory system picks up oxygen in the lungs and drops it off in the tissues, then performs the reserve service for carbon dioxide. The lungs expel the carbon dioxide and bring a new oxygen containing air. Only then both systems are working together can oxygen and carbon dioxide be successfully exchanged between cells and environment. There are many other examples of this cooperation in your body. For instance, the blood in your circulatory system has to receive nutrients from your digestive system and undergo filtration in your kidneys, or it wouldn't be able to sustain the cells of your body and remove the wastes that produced. The circulatory system, direct connection to the lymphatic system, the involvement in defense of organism against infection. The circulatory system is the carrier of chemical information the transport of hormones and other physiological substances on the place of their effect. The muscular system is closely connected to the nervous system. The neurons of the nervous system are connected to most of the cells in the way that all of the cells need oxygen responded by the circulatory system. All of tissues and organs require instructions and direction from the nervous system. There is interaction between the muscles and nervous system. This interaction helps the organism interacts with the environment. At each level of organization, cells, tissues, organs, and organ system structure is closely related to the function. The organism continually interacts with the surroundings and with other systems. In one direction of this interaction, the organism perceives signals arriving from the external world and processes the information content on these signals. The other direction of the interaction is connected with the fact that the life functions are accompanied by various phenomena. These phenomena can be observed and recorded as a signals which supply information and may be processed by the environment. Biological signals. Each living organism produces biological signals. We use the term biological signals to refer to signals originating from a biological entity. A biological signal or biosignal is any signal in living beings that can be continually measured and monitored. Definition: a quantity, biological signal or biosignal is a quantity of matter, change, or quantity carrying or storing information is called as signal. It shows chemical or physical quantities that characterize the property or state of human biological condition. Information is associated with a signal. The signal or information may refer to the state of the system, so to some processes, and so on. There are different types of signals. Parameter of status. Examples are body temperature. The signal associated with this is continuous and its magnitude is approximately constant. The blood sugar concentration is an important indicator of the metabolism. And second type of signals are periodic processes, which describes periodic processes. The ECG, electrocardiogram signal associated with the heart function. There are different types of biomedical signals. There are a lot of different nature of biological signals, such as biochemical signals, different levels of hormones, neurotransmitters, electrical type of signals, potentials, different potentials, and current, physical signals. Examples are pressure or temperature. So human has many types of biological signals. Biological systems are open dynamical systems which are enabled to generate, receive, process, and emit information. Input information reflect the health conditions. Biological signals are generated in live organisms, created by vital manifestation of organisms or by stimulus from external space, which may affect vital manifestation. Velocity changes are characterized by large variability. Mediated biological signals originate by interaction of organisms, for example, with radiation, ultraviolet wave, or with the magnetic field. We use different types of biological signals in diagnostic applications, in diagnostics. Biological signals are a manifestation of activities of very complex biological systems representing real living objects. These signals are generated directly by this object. Biological signals are caused by mechanical, chemical, or electrical activities. So, electrical signals are either the local electrical changes or the generalized electrical changes represented by action potential. Action potentials are the sources of biological signals. They are generated by membranes or muscle fibers. Living body represents a kind of partial conductor. The spreading of APS through such conductor creates the electric field. Scanning electrical signals with different frequency and intensity can be processed and analyzed by various methods to obtain information about living systems or clinical applications. Examples of electrical signals is ECG, EEG. ECG is electrocardiogram, EEG electroencephalogram, EEG electromyogram, ENG electroneurogram. These are examples of electrical signals. Another type of biological signals are non-electrical signals. Non-electrical signals have to be transformed into electrical signals. For example, blood pressure, respiratory pressures, volumes, flows, body temperature. We can measure all these signals by using specific devices. We can measure respiratory pressure, we can measure a blood pressure, by using electromanometers equipped with a pressure transducer working on one of those three principal tensometric, capacitive, inductive. If we need to measure blood flow, we should use electromagnetic flow meter or by the ultrasound detector. Measurement of airflow by pneumatograph, measurement of air volumes by spirometers, measurement of body temperature by thermometer. For all biological signals is possible to record and to control. For recording electrical signals, we use electrodes. We should apply electrodes to the patient's body. We should use amplifier with filters and oscilloscope, chart recorder or computer with AD converter. For recording non-electrical signals, we use transducer, amplifier, chart recorder or computer with AD converter. Biological systems are coordinated and controlled. The concept of control includes two types of processes. Simple control. This is control without feedback, and regulation control with feedback. The two basic functional elements of a control system without feedback are the control unit, control center, and the controlled unit. Each type of control is based on the information transmission. In the control without feedback, no information reaches the controlling unit or center from the controlled unit. Output signal does not react upon the control center. Example, the adaptation of living bodies to their environment, perception of turbulence. Regulation. Regulation is the another type of control with feedback. Biological systems contain many types of regulatory circuits with negative or positive feedback, two different types of feedback. In biological systems, most parameters must stay under control within a narrow range around a certain optimal level under certain environmental conditions. Regulation should be understood as an action which minimalize difference between real regulated values of quantities and their desired values. So different types of feedback are positive and negative. Positive feedback accelerate actions. Feedback loop signals the system is to open and allow more inputs. If we have negative feedback as control, negative feedback decelerate actions. Feedback loop signals the system is to dose and cut off or reduce inputs. This picture shows negative feedback. Negative feedback is a process that happens when the system needs to slow down or completely stop a physiological process. Negative feedback helps to maintain stability in a system in spite of external changes. It is related to homeostasis. Homeostasis, maintenance of nearly constant conditions in the internal environment. Negative feedback occurs when your body temperature begins to rise, and this has to be stopped. At this slide, you see algorithm. How does negative feedback affect and regulates body temperature? If body temperature exceeds 37% degree centigrade, sensors like nerve cells with endings of the skin and brain, then temperature regulatory center in brain, and then sweat glands through body. And negative feedback loop works, and to stop body temperature rise. Positive feedback. Positive feedback is the opposite to negative feedback in that encourages physiological processes or amplifies the action of a system. Positive feedback is a cyclic process that can continue to amplify the body response to a stimulus. Most positive feedbacks provide fast auto excitation of elements of endocrine and nervous systems, in particular in stress responses conditions. Positive feedback play a key role in growth, regulation, and organs development. At this slide, you see the heart rate control example. The impulses generated by the cells of the SA node are carried across the right atrium to the left atrium and to the AV node. The movement of electricity causes the atria to contract, thus helps push down into the ventricles. The electrical signal flows through the His and Purkinje systems. The movement of electricity causes the ventricles to contract and thus to push blood out of the lungs and the rest of the body. The quantity of blood pumped by the heart varies each minute by changing its frequency of beating heart rate or by volume it ejects per beat. In the nervous system, the chemical messengers are neurotransmitters sent straight from one cell to another across a tiny gap. At this slide, you see regulation of heart rate. The control of heart rate is mediated by the autonomic nervous system. The cardiac response to peripheral chemoreceptor stimulation is a result of primary and secondary reflex mechanisms. The secondary influences attenuate the primary reflex effect of the chemoreceptor stimulus on the heart rate. At this slide, you see the normal regulation of blood glucose. Then the blood sugar level rises. The islets of Langerhans in the pancreas release insulin into the blood. Insulin triggers uptake the sugar into the tissues and muscles and triggers the liver to turn glucose into glucagon, which is stored. This brings the blood sugar level down. In the endocrine system, the chemical messengers are hormones released into the blood. Since hormones have to travel through the bloodstream to their targets, the endocrine system usually coordinates processes in a slower time scale that the nervous system in which messages are delivered directly to the target cell. In some cases, such as the fight or flight response to an acute threat, the nervous and endocrine systems work together to produce a response. Homeostasis depends on negative feedback loops. So anything that uh, interferes with the feedback mechanisms can and usually will disrupt homeostasis. In the case of a human body, this may lead to decrease. Diabetes, for example, is a disease caused by a broken feedback loop involving the hormone insulin. The broken feedback loop makes it difficult or impossible for the body to bring high blood sugar down to a healthy level. To appreciate how diabetes occurs, let's take a quick look at the basics of blood sugar regulation. In a healthy person, blood sugar levels are controlled by two hormones, insulin and glucagon. Insulin decreases the concentration of glucose in the blood. After you eat a meal, your blood glucose levels rise, triggering the secretion of insulin from beta cells in the pancreas. Insulin acts as a signal that triggers cells of the body, such as fat and muscle cells, to take up glucose for use as fuel. Insulin also causes glucose to be converted into glycogen, a storage molecule in the liver. Both processes pull sugar out of the blood, bringing blood sugar levels down, reducing insulin secretion, and returning the whole system to homeostasis. Glucagon does the opposite. It increases the concentration of glucose in the blood. If you haven't eaten for a while, your blood glucose levels fall, triggering the release of glucagon from another group of pancreatic cells, the alpha cells. Glucagon acts on the liver, causing glucagon to be broken down into glucose and uh, released into the blood stream, causing blood sugar levels to go back up. This reduces glucagon secretion and brings the system back to homeostasis. Diabetes happens when a person's pancreas can't make enough insulin, or then cells in the body stop responding to insulin, or both. Under these conditions, body cells don't take up glucose uh, readily, so blood sugar levels remain high for a long period of time after a meal. So, at this picture, you see normal regulation of blood glucose. So let's summarize our lecture. views of general system theory are universal. We can apply these basics to all types of systems. General system theory combines isolations, tendencies among engineers, systems analysis, business analytics, IT specialists, and other types of specialists. General system theory offers a framework for understanding all types of system. Benefits of general system theory to design of systems are significant. Theory of general system theory lays at the foundation of much new thinking, in including learning organization, structured analysis, socio-technical design, and strategic planning. We finish with this lecture today. Thank you for attention. So see you during practical classes and see you next time. Bye.